So assume that PB and VB, the wait and signal operations on binary semaphore are provided. Two binary semaphore XB and YB are used to implement the semaphore operation P of S and V of S as follows. Okay, we'll see this one. Okay, let's see what is the meaning of this one. So here the P of S and V of S operation, okay, which is a counting semaphore operation. Okay, what is the meaning of this question is actually we are implementing counting semaphore concept by using what's the binary semaphore concept. Okay, fine. In interview also, if they are asking that can you implement counting semaphore concept by using binary semaphore concept, then you have to say answer is yes. So this is the proof. Okay, fine. See here, P of S and V of S. So these two operation earlier, if you are observing, this is a counting semaphore. So V of S operation, and this is what binary semaphore P of S operation. Sorry, P of S operation counting semaphore and V of S operation counting semaphore. So these two operation P of S and V of S I am implementing by using what's a binary semaphore concept. Binary semaphore concept where PB and VB the down and up operation of binary semaphore, and XB and YB are the values initially binary semaphore is taking. What actually is asking the initial value of XB and YB are respectively what? That means what we need to take respectively, what we need to take initial values of XB and YB initially in a such a way that where it is exactly working like counting semaphore. Okay, fine. Let's see here. I am taking here critical section. Okay, and I am taking S value counting semaphore variable S value as 2. What is the meaning of this one? So inside the critical section, two process should be there according to this counting semaphore concept. Okay, fine. Let's see what will happen. See here, what XB and YB value I need to choose in a such a way that where it is exactly working like counting semaphore. One thing is pakka. So this is XB value, this is YB value. One thing is pakka. Initially XB value cannot be 0, because if it is 0 means what, sir, the first process itself will get blocked by the time it is performing down operation. So one thing is pakka. So option A and B is not a choice, correct choice. Why? Because initial value of XB is 0. Then pakka, sir, XB value initial it should be 1. Okay, fine. Let's see what will be happening. I'm taking option D, which is actually wrong option, but with this you will understand that why C is the correct option. Okay, fine. Let's see, we'll see this. So S value equals to 2. That means two process should be there inside the critical section. So first process is performing down on XB. Possible? Yes, possible. Decreasing this S value to what, sir? 1. Fine. Is 1 is less than 0, sir? Is 1 is less than 0? Okay. Just wait for some time. It is showing some. So initially I am taking XB and YB value as 1, okay, which is actually wrong, but with this you can easily understand that why C is correct. Okay, fine. Let's see, the first process is performing down on XB, decreasing this S value from 2 to 1. Is 1 is less than 0? Answer is no. Then go to the else part, perform upon XB, okay, and enter inside the critical section. When process P1 is there inside the critical section, at this moment process P2 is also trying down on XB. Possible? Answer is what, sir? Yes, it is possible. Decrease this S value to what, sir? 0. Is 0 less than 0? Answer is what, sir? No. Go to the else part, perform upon XB. Fine. And now process P2 is entering inside the critical section. Okay, fine. And a third process is a decision maker. Let's see what will happen. Process P3. It is also performing down on XB. Possible? Possible. Now it is decreasing this S value to what, sir? -1. Okay, fine. Is -1 is less than 0, sir? Answer is yes. Then perform upon XB. Okay, fine. And see here, perform down on YB. See, third process is what, sir? It should not enter. You should block the third process. The reason is what, sir? Because S values 2 means what, sir? 2 process should be there inside the critical section. And we know whenever counting semaphore value is becoming negative, you have to block the process, which we have already learned before this class. Okay, fine. So this pakka as a P3, I need to block this. We know, sir, in up operation, there is no chance of blocking the process. But in the down operation, yes, blocking code is there. Okay, as I have shown you that earlier, whether it is a counting semaphore or binary semaphore, sir, down operation implementation is there. Blocking procedure is there inside the down operation of counting on binary semaphore. There is no blocking in the up operation. I always believe that up operation is what, sir, giving chance. I need to perform P3, you need to perform down on YB. But what is the YB value, sir? 1. So he will successfully perform and process P3 will also enter inside the critical section. Okay, fine. So this is the wrong option because the third process also entering inside the critical section, though the counting semaphore value is 3. Actually, I need to block this third process here itself. Blocking is possible here itself. But to block the third process P3 here, what should be the YB value, sir? YB value should be what, sir? 0. 0. So that's why option C is correct. Okay, so if I am taking xb equals to 1 and yb equals to 0, then it is properly working like what's a counting semaphore. So hope you understood this one. So this is also not, D is not, C is the correct answer. Let's go with the next one. See here. Consider two processes P1 and P2 accessing the shared variable x and y protected by two binary semaphore sx and sy respectively, both initialized to 1. Okay, fine. So that means sx equals to 1, sy equals to 1. P and V denotes the usual semaphore operation actually. Operations where P decrements the semaphore value and V increments the semaphore value. The pseudocode of the P1 and P2 is as follows. In order to avoid deadlock, the correct operation at L1 and L2, L3 and L4 are respectively what? So that means what? If you want to avoid the deadlock, what should be the correct value of L1, L2, L3? Now please pay attention to this. I am trying with A option first. Okay, fine. See here. L1 is this one, L2 is this one, L3 is this one, L4 is this one. L1 and L3 we are focusing first. Okay. So P of Sy. And next one is what's the P of Sx. And this is what's the P of Sx. And this is what's the P of Sy. Okay, so let's see this one. Down on P of Sy, down on P of Sx. These two processes are successfully moving forward. Down on Sx possible, not possible, block. Down on Sy possible, not possible, block. If you are observing why it is not possible, why it is showing the deadlock, I will say only one thing, sir. At the initial level, they have the two variables. They use the two variable at the initial level itself. So that's why they don't have the further variable to show in the further cases. Okay. If further operations are there, their Sx and Sy values becoming what, are already it is 0. So that's why they are unable to proceed further. Okay. So if you want to avoid the deadlock, what is the proper solution for this one? I will say only one thing. Use minimum variable at the initial level. So high chances are that you will not get the block. So like this, in this shortcut, by following this shortcut, you can eliminate the options. See here. Out of two variable, how many variable it is using? L1 and L3? 2. But in option D, if you are observing, it is using only one variable. So option D is the correct answer. Okay, fine. How it is, sir? Can you show this? Yes, bilkul. Why not? Please pay attention. See, I am writing P of Sx. P of Sx. Okay. And P of Sy. P of Sy. So Sx equals to 1, Sy equals to 1. Okay, fine. Now let's see, sir. P1 down on Sx possible? Yes, possible. Okay. And P2 down of Sx possible? Not possible because it is 0. So this process will get blocked here itself. Now P1 down on Sy possible? Yes, possible. Now this process will enter inside the critical section, whatever you are thinking. Why deadlock is not possible, sir? Because at the initial level they spend less variable. That's why, sir, deadlock is here, sir. Less chances are there to have deadlock for this kind of options. Remember this one. Okay, fine. Chaliye. So that's why the option D is correct. Go for the next one. Let's see this one. Suppose we want to synchronize two concurrent processes P and Q using binary semaphores S and T. The code for the processes P and Q is shown below. Okay, fine. The synchronization statements can be inserted only at point W, X, Y, Z. Okay, fine. Which one of the following will always leads to an output string with 00110011? Okay, fine. So which option will give what's our output string as what's a 00110011? This is upon T. Okay, fine. So let's see, sir, which option will give. I am taking option A. I am taking option A. But try to understand before taking option A also. I want, sir, 0011, 0011, 0011. This is the only string because he said that always. So I need to give always this. I need to take always means my code should always give me this string only always. Okay, fine. Let's see what is the meaning of this one. Let's see what is the meaning of this one. That means what, sir? My process should execute PQ, 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 PQ. Then only it is possible. Then only it is possible. But one more thing, sir. By the time P is printing, Q should not execute. That means the door for the Q should be what, sir? Get closed. Keeping the door closed means what for the process PQ? Whatever the operation variable I'm using here for the operation of down operation, that variable value initially should be what's 0. Then only it is possible. Otherwise, it is not possible. Okay. Keeping the binary semaphore value 1 means what's you are keeping door open for the process, and keeping 0 means what's you are closing the door for that process. Remember this one. Okay, fine. So first option I am taking, which is actually wrong. Okay, but at least you will realize that why it is wrong. Okay, fine. Now please pay attention to this. P of S, V of S, P of T, and V of T. S equals to 1 and T equals to 1. That means door is open. The door is open for P and Q both. Okay, fine. Let's see what will happen, sir, if I'm using option A. P is performing down on S and Q is performing down on T. And chances are there, the P is printing 0. I'm preempting this process, this is printing 1. And I'm preempting this process, this is printing 0 and this is 1. Which is not, which is this string is other than this string. That's why it is wrong. Or you may print like this also, 1100 also. Once again, it is violating this string. Getting this idea or not, sir? Why it is happening? Because by keeping because S and T value both are 1. So that's why the door for P and Q both this process door is open. That's why it is happening. Getting this? Getting this? Chalo. Hope you understood this one. So let's see which option is not correct. A is not correct and C is not correct because initial value of S and T is 1. So that means what's the initial value of S should be 1 and T should be 0. So that means the option either can be C also, it can be D also. First I will take D, which is actually wrong. And with this option, you will understand that why B is correct actually. Okay, why B is correct. So you'll get, not only you will get the explanation of the D, but at the same time, you'll get the reason that why B is correct. Okay, fine. Let's see this one. P of S, V of T, P of T, V of T, where S equals to 1, T equals to 0. Okay, fine. So we'll see this. Why this D is wrong? Okay, fine. So anyhow, sir, down on S, possible or not, sir? Yes, possible. If Q is trying means he will get blocked. Why? Because T value is 0. So that's why it is not possible for Q to perform down on T successfully. Okay, fine. Sure. Chalo, next one. Next one. So process P has performed down on S successfully. It is printing 0. Sir, what will happen, sir, if I'm preempting here? Nothing will happen because T values is still 0. So nothing will happen with the Q. You have to come back and you have to print the remaining 0 ops. And it is performing what's up on T. By performing upon T, sir, indirectly is giving chance to process Q. Now Q is performing what's down on T. Now it is printing what's 1 1. Now it is performing what's upon T. That means what, sir? It is giving chance to himself only. It is not giving chance to P actually. And because of this, sir, what you will get this kind of string, sir. Getting this? Fine. Which is actually wrong. Very selfish process. Q is very selfish process. Okay. Actually, after printing the 1 1, the Q should use here V of S instead of V of T. If it is using V of S, so obviously, see here, if I am keeping here V of S, what will happen? Indirectly, we will give chance to what's this one, and because of this, what will happen, sir? After printing 0011, once again it will print 0011 only. So this shows what, sir? B option is correct. How, sir? Here, see here on Z, what it is, sir? V of S is there on Z. Hope you understood that why B is correct. What will happen, sir, if I am taking V of S? Okay, why D is wrong? Okay, fine. So hope you understood this. That's why I said that with this wrong explanation, you will understand that why the B is correct. Okay, chali. Next one. Next one we'll go. Go for this one. Go for this one. This is the common data question. Okay, which of the following will ensure that output string never contains a substring of form 0, 1, 0 and 1, 0 and 1, where n equals to odd. Where n equals to odd. Odd means what? So it can be 1 also, it can be 3 also, it can be any other number which is odd. Okay, fine. Let's see, sorry. See here. When you will get this kind of mixed string, sir. See, if I'm getting this kind of string also 1 1, where 1 power 1 is also this is also one kind of substring. Or if I'm getting like this 1 0 1, when 0 is power 0 power what's 1, this is also one kind of substring. I don't want this kind of substring. But when you will get this kind of mixed substring, sir, whenever the door is open for P and Q, then this kind of mixed string is possible. Sir, where we have discussed this point, sir, here itself. So sorry, I rubbed because I need to explain, but I have shown you, sir, what will happen if this door is open for you. Okay, fine. Once again, I will show you. Let's see what will happen, sir. Let's assume this I am using option A, where S and T values what's are 1 initially. Okay. P of S, V of S, P of T, and it is what's are V of T. Okay. And S and T values what's are 1. Process P is performing down on S and process Q is performing down on T. Both are entering here. Process P is printing 0. I'm preempting this process P, and this process Q is printing 1, and it is printing 0, and it is printing what's are 1. This kind of substring is possible. If you are observing this closely, sir, if you are observing this closely, 1 power 1 is there, sir, where n equals to odd. Yes, you are getting this kind of substring. Or if you are observing this closely, once again, sir, 0 power 1, 1, 0 power 1, 1. So yes, this is also one kind of substring. So that's why, sir, option A is wrong. Okay. Why is wrong, sir? Because reason is very simple, sir. S and T values are 1. So that means door is open for both the process. That's why they're entering, and mixed string also you will get. So that's why, sir, A, B and D is wrong, because initially all these three option has this one. I'm taking C. Let's see what will happen with the C. Why C is correct? The only reason I will say, sir, after seeing this one, C is using only single variable. It is not using T variable. Single variable binary semaphore means what's, sir, at a time only one process can be in active position. Both process cannot be in active position. Remember this point, sir. Okay. How, sir, it is? Can you prove this point? Yes, sir. See it. So this is S. This is S. So S equals to 1. Process P is performing down on S. It is printing 0. Now I'm preempting this process. Preempt, nothing will happen. Why? Because S value 0, Q cannot enter successfully. Okay, fine. Once again, you have to come back 0 print. Upon S. By performing upon S, either you are giving chance to yourself or you are giving chance to Q. Let's assume this I am giving chance to Q. Okay, fine. Now it is performing down on S. It is printing 1. If I am preempting here, sir, nothing will happen. Preempt, because S value 0, P cannot enter. So you have to come back and you have to print like this. Okay, fine. So if you are after performing upon S, either he's giving chance to himself or P. Let's assume this it is giving chance to himself. 1 1 1 1. It is giving chance to P 0 0 0 0. Never ever you will get this kind of substring, whatever we have shown, sir. You'll never ever get this kind of substring. See here. Are you getting this, sir? No, sir. Okay, fine. Because here 0 1 0 is said there. 1 1 0. Okay, fine. 1 0 1. Are you finding anywhere, sir? 1 0 1. No, you are not finding anywhere. See, are you finding here 1 0 1? Answer is no. Okay, fine. So you are not getting this kind of substring. So that's why option C is correct. Hope you understood this one. Okay, chali. Next one, sir. See, after solving these many problems, you will also get some idea about the topic. It is not just I'm completing only 2-3 topic and 2-3 problems and it is over. Because this is a tough one, you know, I also know this one. So that's why I'm spending this much time on this. Okay, Chali, let's see this one. But after today's class, sir, at least you have the idea, some little bit idea about this topic. Let's see this one. A shared variable x initialized to 0 is operated by 4 concurrent processes w, x, y, z as follows. Each of the processes w and x reads x from memory, read x from memory, increment by 1, store it to memory, then terminate. Each of the process y and z read x from memory, decrement by 2, store it to memory, and then terminate. Each process before reading x invokes the p operation, okay, on counting semaphore s, and invokes the v operation on the semaphore s after storing x value to the memory. Semaphore s is initialized to 2. Okay, so what is the maximum possible value of x after all process complete execution? Okay, fine. So x, what is the maximum? Please pay attention. This is very tricky. Means not tricky one, but it is very interesting question, I will say. Okay. First, what I'm going to do, sir, I will convert this question into the WhatsApp table. Okay. Let's see how many process are there. W, X, Y, and Z. Okay, fine. Initially, all these processes are performing down operation based on the given statement. And after this process W and X is reading the X value and incrementing by 1. Okay, chalo, we'll see this one. X value initially is what, sir? 0. Okay, fine. Inside the main memory, X value is what, sir? Is 0. Initialized to 0. Yes. So let's see what W is doing. What actually we want, sir? We want maximum possible value of X. Since he is saying the maximum, please try to understand this one. He's saying the maximum. So what is the trick here? Because first of all, the semaphore is what's the counting semaphore? Because he said that s equals to 2. That is counting semaphore. Okay. And next one is what, sir? X value we have given inside the main memory. How much, sir? 0. So if s is a counting semaphore, means what, sir? At a time, more than one process can be active position because s value is 2 here actually. Okay. S value is 2 here. Okay, fine. Let's see what will happen. The W process is coming performing down on S. Okay. And it is reading this X value and incrementing by 1 and performing upon S. So it is what, sir? 2. And this is process X performing down on S. Just wait for 1 minute. After the Azan, we will complete because if I'm saying anything, you will not get any idea. Okay. Just wait for 1 minute. Thanks. Now we'll continue. See here. Since he's saying maximum, the trick is what, sir? The trick is what? I want to say one thing, because the first thing he has given the counting semaphore, that means more than one process can be in active position. The trick is what, sir? How you can solve this problem within short time? I will say only one thing. Since he said that maximum, start with the positive column. So x value is becoming 1, and here it is becoming what, sir? 2. Okay. But before performing the memory updation, try to preempt this process. Don't execute the memory updation equation. Okay, fine. So that means what, sir? The process X inside is register Rx, it is holding maximum value as 2. Still memory updation you need to perform. So before that only I have preempted this process. Now, sir, whatever the negative column process are there, complete all the process in one go itself. You will get some value. Whatever the value, whether it is a positive or negative, it doesn't matter. But once the process X is coming back, it will restore the Rx value to the memory. Okay, so final value will become what, sir? 2 only. Or much more shorter is what, sir? Since he said that positive, I will say only what, sir? X plus 1 and x plus 1. So it is becoming 1 and it is becoming 2. The answer is 2. Okay, because if I'm adding this negative also, any of the values becoming decreasing only. So this is another shortcut. But anyway, the proper approach is what, sir? Execute all the process. Let's see this one. Since he said maximum, so this process I am starting with what, sir? Positive column. Okay, so x become what, sir? 0 become 1. Now process X. S value is what, sir? 2. Okay. It is setting to 1. And now, sir, inside the main memory, what is X value, sir? 1. Okay. So what it is doing, sir? It is reading this X value inside this register, that is 1, and it is incrementing to 2. But before performing the memory updation, I am preempting this process. That means what, sir? That store MX story, this kind of operation still remain. This is remain still. We need to execute later. Okay, we'll see this one. The concept is very much similar to like where we have discussed in the producer consumer problem. Count equals to count plus 1, count equals to count minus 1. Hope you have remembered that. I was preempting the process before performing the memory updation in the first class. Okay, Chali, next one. Now I will cover all this process Y and Z. Let's see what will happen, sir. Y. What is the current value of S, sir? 1. It is performing down on this one. Yes. Now, sir, inside the main memory, what is the X value, sir? It is still 1. Don't say 2 because 2 is there inside the RX register. 2 is there inside the RX register. You didn't execute this statement. Okay, fine. Remember this one. Okay, chalo. Next one. So it is copying this and decrementing by minus 2. So it is become what? Minus 1 and it is performing upon S. So Y is over. Now Z. S value is 1. It is performing decrementation and inside the main memory it is decreasing by minus 2 means what's this is becoming minus 3. Okay, fine. Perform upon S. Okay, fine. So that means what's W is over, Y is over, Z is over. Now still I need to execute what's X. So inside the main memory, what is the final value, sir? Here it is minus 3, but RX register value, sir, what it is holding, sir, it is 2. So as I said that whenever the process is coming back, it will execute what's the storage operation. Inside the RX register, what it was holding, sir, it was holding 2. So it will paste to the memory 2. Finally, answer what answer you are getting, sir? 2 only. Okay, instead of doing all these things, you can do like this. Okay, as a shortcut I am saying, since it is a counting semaphore, more than one process can be in active position, so you just start with the positive column. Okay, so this is 0 plus 1 1, so 1 plus 1 2, but don't store to the memory, hold inside the register and complete all the negative process. I have see all the negative column processes. I have completed one go itself. I got the minus 3, but whenever this Rx value is coming back, sir, so Rx register value will paste to the WhatsApp memory, so final value you will get WhatsApp 2. Forget about this positive, sir. If it is giving negative value, sir, what can be the answer based on my logic, sir? What can be the answer based on my logic? If it is saying the minimum value, then can anyone write in the chat box, sir? Can anyone write in the chat box what can be the minimum value? Instead of asking the maximum value, if I'm asking what is the minimum value of X after completing all the 4 processes, can anyone write in the chat box, sir? I'm giving you 10 seconds of time. I am giving you 10 seconds of time. Can anyone write in the chat box what can be the negative value? The answer is over. Answer is 2. It is over. Okay, fine. But try to visualize this concept. because this question he will not repeat, but the concept he may repeat. Can anyone? Can anyone? Okay, answer is what, sir? -4. Maybe some of you are calculated also, but you are thinking that why should I type? Okay, fine. Let's see, sir, here how it is. Start with the negative column. So this is becoming what's a 0 -2 -2. Okay, and this is becoming what's a -4. So hold inside the RY register -4. And before performing the memory updation, preempt this process and complete all the positive column processes one go itself. Okay, you will get one value, but anyhow, sir, who will become winner, sir, in the context of the synchronization, whichever process coming in the last. Okay, fine. Here RY coming in the last, sir, whatever the value is there inside the RY register, it will paste. So finally you will get what, sir? -4. Understood this? Okay, fine. So this is some tricks to solve this kind of questions. I have seen so many test series where there are people are asking this kind of questions. Okay, fine. But try to understand the logic behind this one. You can, with which you can easily solve this question. Okay, fine. Chali, next one. But if I'm asking you one more question, can I ask one question? Okay, fine. Forget about the counting semaphore concept, sir. If S is a binary semaphore value, forget about the maximum and minimum. What can be the final value of X? Can anyone? What can be the final value of X if S is a binary semaphore? Can anyone? Maybe you may be thinking, sir, what can it can be? See, this kind of things you need to learn actually. Answer is what, sir? In first of all, if it is a binary semaphore, at a time only one process will be in active position. The other process cannot be in active position. Getting this idea? Fine, chili. And because of this, what will happen, sir? X value will become 1 and 1 will become 2 because other process it cannot come inside this one, and where it is reading and performing some any other action until unless the earlier process is not finishing its execution. See here, S equals to 1. So how many processes will get activated, sir? Only W. Any one process. Let's see W. It is performing 0. So X value is becoming what's a 0 to 1. So by the time it is incrementing, is there any other process who can successfully read the X value? Answer is no, because S value is 0. So no one can read the X value and increment or decrement. Get inside or not, sir? Fine. So it is becoming 1. Fine. And it is becoming 2. And 2 minus 2, what's, sir? How much? 0. And 0 minus 2 minus 2. The final value is what, sir? -2. If it is binary semaphore, I am not asking it is a maximum or minimum value. Okay, I am saying, sir, what can be the final value of X? It is what, sir? -2 if it is a binary semaphore. If it is a counting semaphore, since he said that maximum value, so that is 2. If it is saying minimum value along with the counting semaphore, S value as 2. So what is the answer for this one, sir? -2 answer for this one. Okay, one question, so many analysis. Let's see this one, sir. Okay, let's see this one. Okay, chalo. Please pay attention to this. Each of a set of n processes, I think it is asked in 21 or something, this question. Okay, 20, 20. Here it is there. Okay, chali. Next one, sir. Each of a set of n processes execute the following code using two semaphore A and B initialized to what, sir? Initialized to what, sir? A equals to 1 and B equals to what, sir? 0 respectively. Assume that count is a shared variable initialized to 0 and not used in the code P. So inside this P, there is no count variable. So what is the count value initially? 0. Okay, fine. Let's see what can be the answer for this one. What does the code achieve? Okay, it ensures that no process execute code section Q before every process has finished code section P. Let's see, sir, whether it is possible or not. Okay. Chalo. Chalo. We'll see this one. I'm taking uh, n value, because he said that n process, n equals to 3 I am taking. Assume this 3 processes are there, P1, P2, P3. If you want, you can take more than that also. Okay, fine. It's totally up to you. But as many you are taking, that much you are wasting your time. Okay, fine. Let's see here. Process P1 is coming, performing down on A. Possible? Yes, possible. It is incrementing this count value to what, sir? 1. Yes, sir. Okay, fine. Next one. Count value is what, sir? Right now it is 1. 1 equals to 3, sir. Answer is no. Then skip this statement and execute this one. Signal on A. That means 0 is becoming 1. Wait on B. So B value is what, sir? Right now it is 0. So that means what, sir? Whenever you are performing binary semaphore variable value is 0. And if you are performing down means what, sir? You will get blocked. So that means what, sir? The queue which is related with this binary semaphore variable inside this queue, process P1 is there. Got blocked. Okay, fine. Next one. Process P2 is coming, performing down on A. Fine. Incrementing this count value to 2. Fine. Is 2 equals to 3, sir? Answer is no. Then skip this statement and perform upon A. Fine. Wait on B. B value is what, sir? 0. So that means process P2 will also get blocked. Now, third process coming, sir, performing down on A. Possible? Yes, possible. Incrementing this count value to what, sir? 3. Yes. Is 3 equals to 3, sir? Answer is yes. Now, signal on B. Signal on B. So, whenever you are performing signal according to the binary semaphore, the first condition what you are checking, sir, whether queue is empty or not, sir. If queue is not empty, then select a block process from the queue and wake up. If queue is empty, then you are going to the else part and you are resetting this binary semaphore value from 0 to 1. But right now, sir, by the time you are performing signal on this B, you are finding, sir, queue is not empty. So you are unblocking process P1. You are unblocking process P1 and process P3 is performing signal on A. Fine. Wait on B. So B value is 0. So process P3 will get blocked here. But since process P1 is unblocked, so it is performing what, sir? Once again signal on B. So that means it is unblocking to process P2. Okay, fine. Now process P2 is also performing signal on B. That means process P2 is unblocking process P3 and process P3 is setting this B values from 0 to 1 because queue is empty. And finally, sir, these three processes can execute at the same time. P1, P2, P3, this code section queue. This is possible. So that means what, sir? It ensured that no process execute code section queue before every process has finished code section P. Obviously, see, code section P only, after the completion of code section P only, I have taken this assumption. Okay, fine. So everyone can execute the code section P before executing the code section Q. Okay, fine. Yes, it is true. Okay, next one, sir. It ensured that two processes are in code section Q at any time. Is this possible, sir? No, sir. Here three processes can be there inside the code section Q, which we have just seen this one. Okay, fine. It ensured that all the processes execute code section P mutually exclusive. No, it is not guaranteed. Why? Because here he has not mentioned the concept of binary semaphore or such kind of things inside the code section P, where I can give you guarantee that at a time only one process will execute. No, it is not possible. Okay, fine. It ensured that at most n-1 process are in code section P at any time. How you can give guarantee for this one, sir? There is no guarantee because for that you have to use some counting or some other approaches you have to use. But we don't know what is there inside the P. So that's why it is not possible. You cannot give that this is the guarantee here in code section P. Okay, fine. So that's why the option A is correct. The next one. Go with this one, sir. Consider the following threads T1, T2, T3, and this is, I think, 23 or something. Okay. 22. So, next one. Consider the following threads T1, T2, T3 executing on a single processor, synchronized using three binary semaphore variable S1, S2, S3 operated upon using standard wait and signal operation. The threads can be context switch in any order at any time. ठीक है चलिए. Which initialization of semaphore would print the sequence BCA, BCA, BCA? I want BCA, BCA, BCA. So that means what, sir? If you are observing closely, B is printing by thread 2, C is printing by this one, and A. So that means we need to execute T2, T1, and T3. And once again, I need to repeat what's a T2, T1, T3 like this. Then only I will get BCA, 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 BCA like this. Okay, fine. Now please pay attention to this. If I want to ensure that I need to print B successfully, so initial value of S1 should be what, sir? S1 initial value S1 should be what, sir? 1. And by the time T2 is printing B, At that time, T1 and T3 should not get print. Because if they are printing means what's the chances are there after B, maybe A also can come. Chances are there. Or before B itself, it may get print A also. Possibility is there. So that means by the time T2 is printing, at that point of time, T1 and T3 should not get executed. To block T1 and T3, sir, the initial value of S3 and S2, what actually I need to keep, sir? 0 only. That means I need to close the door for T1 and T3. And initially I need to open the door for what's a T2. So that's why, sir, S1 is 1, S2 is 0, and S3 is what's a 0. So where it is, sir? Option C is correct. But let's see how it is. Okay, fine. Let's see how it is. T2 is executing what's a down on S1. Possible? Yes, possible. It is printing B. By the time it is printing B, sir, is this possible for T1 and T3 to execute S2 and S3 successfully? Answer is no. Why? Because S values are 0. Understood this? Fine, Chali. So that's why, sir, B printing. And after this one, if you are observing, since I want to print C, so that's why it is using S3, signal on S3. That means by saying that signal on S3 indirectly, it is opening the door for T1. Okay. So S3 is becoming what, sir? 1. Now T1 is performing down on S3. Okay. And it is printing C. And now it is performing what's a signal on S2. S2 is what's a here. So that means by performing signal on S2 indirectly, it is opening the door for what's a T3. Getting this idea or not? So it is becoming 1. Now T3. So by the time T3 is printing, is this possible for T1 and T2 to print? Answer is no, because S1 and S3 values are 0. So that's why it is not possible. So it is down on S2. Print A. Okay, fine. And signal on S1. That means what side is 1. So by performing signal on one side, indirectly is giving chance to T. So T2. So once again, the cycle is going to get repeated. Okay, so you have already got the BCA. Once again, BCA, BCA, BCA. So best option is what's a C. Hope you understood this one. Okay. So next one. Now we'll learn memory management, sir. We'll learn memory management. Okay. Let's see what is happening. So sufficient questions we have discussed. Though it is a revision class, but still I ensure that I have discussed sufficient questions to give the clarity about the synchronization. Now we'll see, sir, memory management. Another good topic in context of operating system. You'll see this one. The functionality of memory managers. What is the functionality of the memory manager? Allocating and deallocating the memory to the process, free space management, and etc. The main thing is what's here? Goals, which we need to have the clarity here. Okay, fine. Efficient utilization of memory by minimizing internal and external fragmentation. Fragmentation means what's the wastage of memory. We'll see what is the internal fragmentation and external fragmentation within short period of time. The second one, to run larger process by using a small memory. So first I will explain this goal, which is actually related with the virtual memory. Okay, see here. This is your 1 GB RAM. And you have the process of sizes what's are 4 GB. The question is this one, sir, how you will execute 4 GB process by using 1 GB RAM? Okay, it is looking impossible. Okay, fine. But what actually we are doing, sir, we are dividing this process into the pages like this. And initially, whatever the pages required for the execution, those pages I am keeping inside the main memory, and the rest of the pages I am keeping on hard disk. Where on hard disk, sir? In that the logical address is space. Okay. Now CPU is executing page 0, page 1, page 2, page 3. After this, CPU want to execute page 4. Is that available inside the main memory? Answer is no. This is called page fault. This is called what, sir? Page fault. Okay. Sorry. This is called what's a page fault. Okay, fine. Once since P4 is not there, so this is called page fault. So what will happen? Operating system will go to the hard disk, it will bring the required page and it will keep inside the main memory. Okay. If page 4 is also finishing, means once again, one more page fault, operating system will go to the hard disk, bring that required page and keep inside the main memory. So in this way, sir, based on the demand, you are going to the hard disk and bringing the required page and keeping inside the main memory and executing. So in this way, sir, you are executing a process whose size is greater than the what's our main memory, whose size is greater than the main memory. Okay, so that means by small, based on the demand, operating system is going to the hard disk, bringing the required page and executing. Okay, fine. Next one. So first we need to concentrate here, sir. This goal is related to what's the virtual memory. If time permits, I will touch virtual memory because hardly we have the 1 hour. So in this 1 hour, I will cover as many things as possible. More than little bit, 1 hour 10 minutes is remain. Okay, for us. Let's go for the next one. First. Memory management technique, please pay attention, is classified into two parts: contiguous non-contiguous. Contiguous is further classified into two parts: fixed partition skill and next one is variable partition skill. Non-contiguous means what, sir? Paging, multi-level paging, virtual memory, segmentation. Okay, fine. So let's see how to understand this one, sir. The first, before proceeding towards the fixed and variable and all those things, try to understand this. What is the meaning of contiguous and non-contiguous? Okay, try to understand this one. Okay, what is the meaning of contiguous is what, sir? Inside the main memory, this is main memory where partitions are there. I am keeping one process. I am keeping all the instructions which is related to the one process continuously in the one location. This is called what's a contiguous. Normally people say one partition equals to one process, but I say that all the instructions which is related to the process keep in the one location of the memory. That is called what's a contiguous. Okay, fine. Chali. So that means what, sir? You want to say that non-contiguous means all the instructions which is related with the process, they are not available in the one location of the main memory. Is it correct? Answer is yes. Let's see here. Okay, this is the main memory. Okay, chalo. So let's assume this partition size is 1 MB and all the partitions are of equal size. Already some process are there inside the main memory which captures some frames. Okay, fine. So what I'm doing, sir, this process size is 3 MB. My partition size is what's our 1 MB frame size. So I'm dividing this into the what's our pages. Okay, and page size equals to what's our, normally what we are saying, page size equals to frame size. The reason is what's our, because this chunk of the process which I am saying as a page, I need to keep inside the main memory. So page 0 is here, page 1 is here, and page 2 is here. Getting this idea? Fine. Chali. So now if I am keeping all these three pages, now please tell me the instruction which is related with the page 0, I0 and I1 is here, I2 and I3 is here, I4 and I5 is here. Are you finding all the instruction which is related with the process continuously in the one location of the main memory? Answer is no. So this approach is called what's a non-contiguous. Have the clarity on this. Okay, fine. So we'll see the first one, fixed partition skill. Fixed partition skill first. Fixed partition scheme is what, sir? Number of partitions are fixed. Sizes can be anything. Okay, fine. So this is happening at the booting time itself. Whenever you are booting operating system, at that time itself, we are dividing what do you say this main memory into the partitions. Okay, and this is a static approach, because before executing any process, we are dividing this main memory into the partition. Okay, fine. So let's see here. This is main memory, and inside the main memory, I am changing color. Process P1 is here. Let's assume this process P1 size is what, sir? 10 KB. That's why I kept it here. So yeah, in this way, I kept a few process inside the main memory. What is the rule actually we are using here is one partition equals to one process. Okay. Let's see performance of this one. Performance of this one. The first one is internal fragmentation, whether it is there or not, sir. What is the meaning of internal fragmentation, sir? Fragmentation means what's the wastage of memory? Internal fragmentation means wastage of memory within the partition. Wastage of memory within the partition. So let's assume this. After some time, process P3 completed its execution. Fine. And I brought another process P6, whose size is what's that? 25 KB. I'm keeping process P6 here. So how much space it is capturing, sir? 25 KB. So 5K is going waste. So this is called what, sir? Internal fragmentation. Because rule is what, sir? One partition equals to one process. Getting this idea? Fine. Chali. So internal fragmentation is there? Yes, sir. What is the meaning of internal fragmentation, sir? Wastage of memory within the partition. That is internal fragmentation. Next one. Degree of multi-programming. Degree of multi-programming is, please tell me, is it limited by the number of partitions or it is unlimited? Yes, it is limited by the number of partitions. See here, how many partitions are there, sir? 5 partitions are there. So more than 5 processes you cannot keep inside the main memory. So that means degree of multi-programming is limited by number of partitions. Okay, fine. Next one. Maximum process size equals to maximum partition size. You cannot keep a process whose size is greater than the 50K. So these are the things which we found some issues in the fixed partition scheme. Let's see, sir, how to solve this one. So that's why to solve this one, sir, we are moving towards a variable partition scheme. Let's see what will happen in the variable partition scheme. Variable partition scheme. The first one is here. Initially is what, sir? Memory is a large free chunk in the variable partition scheme. Initially, memory is a large free chunk in the variable partition scheme. Based on the incoming process size, I am creating the partition dynamically inside the main memory. Let's assume this process P1 size is 10 KB. I am keeping process P1 here. I have created the partition of size 10 KB. Another process is 15 KB. In the same way, other partitions also have created like this. Sure. Let's see performance of this one. We are not using first thing, we are not using that rule one partition equals to one process here. Okay, fine. So remember the performance. Let's see performance of this. The first one, internal fragmentation. It is there or not? The internal fragmentation, it is there or not? It is not there. Why, sir? Because based on the incoming process size, we are creating the partitions inside the main memory. So there is no chance of internal fragmentation. Second one, sir. Maximum process size. Maximum process size equals to memory size. Memory size. Okay, fine. So that means what's let's assume this initially, since initially memory is a large free chunk, the first process, let's assume this your memory size is 1 GB and the first process size itself is a 1 GB. So obviously you will keep that process inside the main memory. So that's why maximum process size equals to what's the memory size. Third one, degree of multi-programming. Earlier in earlier approach, it was limited by the number of partition, but here, sir, let's see what will happen, sir. Let's assume this. After some time, process P4 is finishing its execution. Okay, fine. And what I'm doing, sir, another 3 process I'm taking whose size is what, sir? 10 KB, 10 KB, and 10 KB. So can I keep here? Answer is yes. So earlier the degree of multi-programming was what, sir? 4. Now it is becoming suddenly 6 because this upper 3 and this new 3. Okay, fine. If the incoming process size, if I am taking as instead of 10 KB, 10 KB, if I am taking 5 KB, 5 KB, then I can keep 6 processes inside the main memory. So 6 and older ones, what's the 3? 9. So that means what's the one thing is pakka. If the incoming process sizes are small, then degree of multi-programming is increasing. If the incoming process size is big, then degree of multi-programming is what's decreasing. In overall cases, sir, the degree of multi-programming is not limited. Not limited. Hope you understood this. So that means next one, fourth one. What is fourth one, sir? External fragmentation. External fragmentation is there or not? We'll see. Okay. So what actually we are doing for the external fragmentation? Let's assume this process P4 has finished its execution. Process P2 has also finished its execution. This 15K, this 30K is freely available. Another process P5 is coming, sir, whose size is what, sir? 35 KB. Where you will keep this process, sir? Collectively, you have the 45 KB space, but still you cannot allocate memory to the process P5. Why? Because it is asking 35 KB, which we don't have continuous manner. Though the available space is more than the requesting process size, here 45 is there, sir, collectively, and it is asking 35. Though the available space is more than the requesting process size, but still it is not possible for us to allocate memory to the requesting process because available space is not in contiguous fashion. It is not in contiguous fashion. That means what's the external fragmentation is there? Answer is yes, it is there. Okay, fine. Next one. How to overcome this issue? Then actually what we are doing, sir, to overcome this issue, because see, earlier 3 issues we have overcome, but we got the new issue, that is external fragmentation. Okay, fine. So someone suggests that please move all this process P1 and P3, whatever the process are there inside the main memory, move all those processes one side of the main memory. Obviously, other side of the main memory, you will get the large free chunk. Okay, fine. So like this. P1 and P3. So how much chunk I am getting, sir? 45 KB I am getting. Now, can you allocate to 35? Answer is yes. So this mechanism is called what's a compaction. Compaction. But compaction is an expensive approach because nothing is free. How you can move process from one side to one location to the other location? It requires lots of CPU cycle. So that's why compaction is what's an expensive approach. So what actually they have done, sir? They started thinking that compaction, it is a solution for the external fragmentation, but it is an expensive approach. Now they started thinking that, is there any approach through which I can solve the external fragmentation? Then they realized that why we are getting the external fragmentation, because the available space is not in contiguous approach, non-contiguously it is available. Then they started thinking that why don't we design a technique that itself is a non-contiguous? Once again, I'm repeating, sir, why don't we design such kind of technique that itself is a non-contiguous? So see here, so that's why, sir, they have moved towards the paging concept. Okay, what is happening in the paging, sir? Wherever the free partition I am getting, there I am keeping my pages. It doesn't matter for me where that space is available, whether it is available inside the main memory or not. It is that's it. Okay, fine. So this is the beauty of what's a paging, non-contiguous. So that means what's if someone is asking why you are using paging, means what's the reason is because I want to avoid external fragmentation issue. Okay, and one more thing. Segmentation is also non-contiguous approach, but it has an external fragmentation issue. which you are solving by through extra paging on the segmentation issue. Okay, fine. So remember, sir. So why we are moving towards the paging, sir? Because to avoid the external fragmentation. Okay, it is one of the non-continuous approach in interview. Because see, non-continuous approach we are remembering like this. Okay, non-continuous means what, sir? There is no external fragmentation issue. But if someone is asking in the interview, is there any technique where the technique is a non-contiguous but it has an external fragmentation? Then you have to say sir segmentation. Okay, fine, sure. Let's see sir something else. See, this is not only for useful for the gate, even for the interview also it will be very useful for you. Partition allocation methods we'll see. See here. 20K, 30K, 40K. Though I'm writing K, but assume KB, because it will take some time for me to write in. Okay, so KB. Okay, chali. Next one. These four partitions are there. Now process P1 is coming, sir, whose size is 5 KB. Now where you will keep this process? Where you will keep this process? I know most of you will say, sir, 10K. I know this. But the best answer is what, sir? We cannot say. Why? Because all the partitions are eligible to accommodate this process P1. The process P1 size is what's are 5 KB. And all the partitions have size the what's are more than 5 KB. Easily anyone can accommodate. Then which partition should accommodate this processor is totally depend on the algorithm. What algorithm actually we are using. If I'm using first fit, obviously 10 KB. If I'm using worst fit, obviously 40 KB. So here answer itself is changing because algorithm is changing. Understood this? Okay, chali. Next one. Please pay attention to this. Okay. Let's see what will happen if I'm using first fit. First fit. I am taking a process P1 whose size is 25 KB. Okay. If I will check in which partition I will keep this process P1 if I'm using first fit, best fit, worst fit, next fit, like that we'll check. Okay, fine. Let's see this one. First fit. What is the meaning of first fit, sir? Start searching from top of the memory and allocate first free sufficient partition. So I'm starting searching from the top of the memory and allocate first free sufficient word is very important. The sufficient word is very important. Okay, fine. Let's see, sir, this one, what will happen. Is this free? Yes, but not sufficient. But not sufficient. Is this free? Yes, but not sufficient. Is this free? Yes, and sufficient also. That means if I'm using first fit, I will keep in the 30 KB. Okay, next one, sir. Best fit. Allocate smallest free sufficient partition among the available partition. Okay, fine. Let's see, sir. According to the best fit, see 10 KB, 20 KB is not eligible. These four partitions are there. Out of this 4, 30, 40, 50, 60, which one is the smallest one, sir? 30. The next one, worst fit. Allocate largest free sufficient partition among the available free partition. So please tell me which one is the largest free sufficient? 60 KB. Next fit. It is also working like first fit, but start searching from the last allocation. Let's assume this last allocation somewhere you made. Somewhere you made here. Okay, now start searching from the next one. Is 20 is sufficient? Not sufficient. Free but not sufficient. Is 30 is sufficient? Answer is yes. So that means what's sufficient? Okay, hope you understood this one. Chalo. Now you try this one. Slowly we are coming towards the paging also. Okay. Consider the following figure in which blank regions are not in use and hatch regions are in use. Okay, fine. The sequence of the request for the blocks of sizes, this one can be satisfied if you use variable partition scheme. So just these are the requests and this is the memory. Which algorithm you can satisfy, sir? First fit or best fit? We need to check. Okay, fine. First, I will try with the first fit. First process coming, sir, whose size is 300K. And he has already given, sir, arrow left to right. So I am to start searching from here. Is this free? Yes. But is this sufficient to accommodate? No. Then move forward. Is this free? Yes. And sufficient also. So 300 I am keeping here. I remain with what, sir? 50K. 25. So don't start searching from here. It is not next fit. Okay, it is the first fit. Once again, you have to start from the top. So is this free? Yes. And sufficient also. So you remain with what, sir? 125. 125. Once again, sir, here itself you can satisfy. 50. You don't have other choice other than this. So that means what, sir? First fit is possible. First fit is possible. Okay, fine. So let's see with the best fit it is possible or not. So 3. Let's say this one. Best one. Best fit means what? Is allocate smallest free sufficient. 300 means what, sir? This is the smallest one free sufficient. So 300 you are keeping here and 50K remain. 25 is what, sir? This is 150, this is 50. So obviously 25K. So remain with what, sir? 25K. 125. Obviously I'm keeping here. I don't have any other choice other than this. So I remain with what, sir? 25K. 50. How much space is there, sir? 50, 25K and 25K. Collectively, it is a 50K space. But still, it is not possible for you to allocate memory to this process. The reason is what, sir? The available space is not in contiguous fashion. That means what, sir? It is an external fragmentation issue. Understood this? So that means what, sir? What is the best answer for this one? First bit, but not best fit. Answer is B. Go with this one. Read first this one, 2015. Read this one carefully. First read. At least you have some data in your mind. Over, chalo, we'll see. Consider 6 memory partition. So 1, 2, 3, 4, 5, 6 of sizes. So I'm changing my color because everything is looking like yellow only. Okay, fine. So 200 KB, 400 KB, 500 KB. And 250 KB. Okay, fine. So where K refers to kilobyte, these partitions need to be allotted to the four processes of size 350, 210, 468, 491. Okay, in that order. If the best fit algorithm is used, which partitions are not allotted to any process, use fixed partition scheme. Okay, fine. See, $357 best fit. So obviously, according to the best fit, 357 means this is 357. I'll change my color. Next, 210. 210 means what's are obviously 250. Next, 468. Other than this, we don't have any other choice. Next one is what's are 491. Other than this, we don't have any other choice. Okay, fine. Next one, sir. So you remain with what's are 200 and 350. So what is here, sir? If the best fit algorithm is used, which partitions are not allotted? So answer is what's are 200 and 300. So 200 and 300 partitions are not allotted. Okay, 2015 question. Next one, sir. Now move towards the pages. Now move towards the page. Okay, read this carefully first. We have covered so many things within 4 hours of session. Earlier, first session was 2 hours. Now this is 2 hours. So we have completed so many things. Okay, fine. चलो see, CPU generates logical addresses. With the generated logical address, it is not possible for CPU to interact with the main memory because main memory has physical addresses. Therefore, we require a mapping technique which can convert these logical addresses into physical addresses. This technique is named as paging. Okay. See, paging has so many definitions. Like you can say dividing a process into the pages is called paging, or bringing the pages or swapping out the pages, like bringing the pages from hard disk to the main memory and swapping out from main memory to hard disk. It is also called as paging because you are dealing with the pages. Okay. But generally, I prefer this definition. The reason is what, sir? It is very much matching with the architecture of the paging. That's why. Okay, fine. So what will happen here? CPU generates the logical address and main memory has what's a physical address. So it is not possible for you to interact with the main memory. So therefore, what paging does, sir, it will take this logical address and it will convert into the physical address. Then this mapping technique is named as what's a paging. Okay, fine. Chali, we'll see this one. Now, sir, next 10 minutes, don't do anything because it is necessary to focus to you. Okay, it is necessary for you to focus here. Okay, Chali. This is CPU, n-bit CPU, like 16-bit, 32-bit, like that. And maximum process which you can run is WhatsApp 2 power n size, 2 power n size. Okay, so and this is main memory, which is already divided into the frames. And assume that already some process are there inside the main memory which has already captured this some frames. Okay, fine. Now let's see what will happen. Sorry. Let's assume this all the frames are of equal size and one frame size equals to what, sir? 1 MB I am taking, and this process size I am taking as 4 MB. Is it possible for you to keep this process inside the main memory? And this 2 power n is also called as what's a logical address space or virtual address space. Because if process is there, at the time of execution, we are adding the addresses also with that. Okay, fine. So collection of all those logical addresses is called logical address space. If you want to imagine the process in terms of addresses, you can say a logical address space. So that's why, sir, many times we are observing that sometimes we are saying logical address space, sometimes we are saying process also. Okay, fine. Chalo. See, so it is 4 MB and it is 1 MB. So it is not possible for you to keep this process inside the main memory. So what I am doing, sir, I am dividing this process into the WhatsApp pages. And each page size equals to WhatsApp frame size. Hope you understood that why we are taking page size equals to frame size. The reason is WhatsApp, the chunk of the process I want to keep inside the main memory. So main memory will never ever compromise on the process. Main memory will say if you want to keep something in me, you have to compromise. Okay, fine. So we are dividing this into the pages, page 0, page 1, page 2, page 3, like this. And initially, okay, so these 4 pages are there. I'm keeping this page 0 here, page 1 here, page 2 here, page 3 here. Okay, fine. And inside the main memory, I kept these pages wherever I got the free frames. And the information about these pages I am maintaining inside the page table like this. Page 0, where it is, sir? Frame 1, page 1, frame 4, page frame 5, frame 7. Okay, fine. Like this, we are keeping inside the page table. Chalo. So that means wherever the pages are there, that information I am maintaining inside the page table. So that's why, sir, in the formula, whenever you are calculating the page table size, the number of entries inside the page table equals to what's the number of pages in a process. Number of pages in a process we are saying. 4 pages you are keeping inside the main memory, and 4 entries are there. And one more thing. Sometimes what students are doing, they are thinking this F1 means what, sir? I am keeping here total frame here, this frame inside this page table. No, never ever think like that. this is your house, this is your house, and this is your house address. I am keeping your house address, not house itself. Okay, this is the meaning of this. Let's see, sir, some more thing. Anyhow, so it is happening. So it is happening with what's one process, but we have the multiple process. Like here, process M0 is there, process M2, M1 is there, process M2 is there, because we are dealing with the multiple programming. Let's see how CPU is dealing with the multiple processes. Now, sir, please tell me, if you have three processes inside the main memory, all these three processes is CPU is executing at the same time? Answer is no. It is selecting one process at a time. Let's assume this, it has selected M0. But we know, sir, process is already divided into the WhatsApp pages. So that's why, sir, it has page 0, page 1, page 2, page 3. Okay, like this. Now, please tell me, if CPU is executing one process at a time, that process is already divided into the pages. Is CPU is executing all the pages of that process at the same time? Answer is no. CPU is taking one page at a time, like page 0. Okay, fine. And inside the page, sir, I0, I1, I2, I3. So these instructions are there and some addresses are there. Now, if you want to execute the instruction 0, and before that one, inside the page 0, we have the multiple instructions. Okay, multiple instruction. Now, if CPU is executing all the instruction of the process at the same time, all the instruction of the page at the same time, or it is executing one instruction of the page? Answer is what, sir? It will execute one instruction of the page at a time. Why? Because CPU has only one instruction register. Okay, suppose this CPU want to execute the instruction number 0. So this is the address, page number 0, word number 00. Instruction number 1, page number 0, word number 01. Okay, fine. So this is called actually logical address. This is called actually what's a logical address. Hope you understood this one. Okay. So that means what's a, if inside the one page, if you have the 4 instruction or 4 words or 4 location also, you can say, means 4 logical address you are generating. Never ever think that for one page you are generating one logical address. Remember this one. Okay, fine. So let's see how to understand this paging concept. Simple page. CPU is generating the logical address, which is collection of binary bits and which is divided into two parts, P and D, where P is indicating the page number and D is indicating the word number within that page, which instruction actually you want to execute within that page. Okay, fine. That is the meaning. But anyhow, sir, first I will design this. It will take some time for me to design. And this is the main memory, which is divided into the equal size partitions or frames also you can say. Okay. Let's assume this already some process are there inside the main memory and they have captured some frame. So now I kept a few, like I have divided logical address into the WhatsApp pages. Those pages I kept inside the main memory, like page 0 here, page 1 here, page 2 here, page 3 here I kept. Okay. And the information about these pages I am maintaining inside the page table. Okay. Inside this page table, I am maintaining this information: page 0, page 1, page 2, page 3. Page 0 where it is F0, page 1 F3, and this is F5, and this is what's the F8. Okay, fine. Now, sir, CPU generating the logical address where it is saying that I want to access page number 0, and within that page number 0, I want to access word number 00. With this logical address, the first thing, CPU is referring to the WhatsApp page table. And from here, it has taken out what's the frame number, that is F0. But taking out the frame number is not a proper solution, because inside this frame 0, page 0 is there, and page has what's the number of instruction. Like it has some instruction like I0, I1, I2, I3. So 0, 0, 0, 1, 1, 0, 1, 1. Okay, fine. So let's say, sir, what will happen? So you have to add this D also, 0, 0. So with this physical address, you are referring to this one. Okay. And the word number 0, 0 you want to access, that means instruction number I0. So reach to the frame number 0, and inside that frame number 0, you have the 4 instruction. Which word or instruction you want to access, sir, it is indicated by this one. So that is what's the 0, 0. So that means what's the answer is I0. I0. So this is simple paging architecture. Simple paging architecture. Okay, fine. So what is the, let's see, performance of this one. Effective memory access time equals to what, sir? M plus N. Where this page table is available, sir? Inside the main memory. So first you are referring to the what's the page table that is taking some M access amount of time, and once again you are finally you are referring to the main memory to access that data. So 2 times you are accessing the main memory. Okay, fine. So this is simple paging architecture. Now a few questions are there for this one. Not questions, I will say, sir, some important points are there. I'm saying like this. Okay, paging is applied with the respect to each process, because if I'm writing it will take lots of time, and I have already given in notes itself. Okay, if you have seen my lecture, it is there, but anyway I will tell you. Okay, fine. If you want to make notes, you can make this one. Paging is applied with respect to what's each process. So therefore each process has its own page table. If 10 processes are there, means 10 page table are there. Okay, fine. Next one. The page table of the process stored in main memory. Where it is there, sir? In main memory. Fine. Next one. Are you finding external fragmentation in the paging? Answer is no. External fragmentation was the reason why we have shifted towards the paging. No. Are you finding internal fragmentation in the paging? Yes, it may be there, but in the last page of the process. Last page of the process. How, sir, it is? See here. If I'm taking my process size as equals to 9 KB, my page size equals to what, sir? 2 KB. Then how many pages required to store this process, sir? 5 pages. So each page size equals to 2 KB, 2 KB, 2 KB, 2 KB, 2 KB, 8 KB is over. In the last page, half page I am filling. So that means what's the last 1 KB is going waste. So that is called what's the internal fragmentation. Okay, fine. Chali. The next one is, the question is this one. Question is this one. According to the simple level paging, sir, don't you think, sir, simple level paging is avoiding the problem of external fragmentation? It is okay, but it is very slow, because 2 times you are accessing the main memory. To access the one instruction, how many times CPU is referring to the main memory? 2 times. For CPU, referring 1 time main memory itself is a slow, because normally we are taking the CPU speed like in terms of nanosecond. 1 nanosecond equals to 10 power minus 9. And CPU and main memory access time I am taking in terms of microsecond. 1 microsecond equals to 10 power minus 6. So huge speed mismatch is there in between main memory and what's the CPU. Accessing 1 time itself is a slow for the CPU. If CPU is accessing 1 time to the main memory, it's slow approach. But you are asking to access main memory 2 times to the CPU. It is much more slow. The question is this one, sir. How you can improve this performance? How you can improve this performance? To improve this performance, what actually we are doing, sir? We have added another component here, which is called TLB, translation look aside buffer. Okay, what is this one, sir? It is made up of some associative registers. It is a small chip which is made up of some associative registers which you are finding beside the CPU. Okay, and here page number and frame numbers are there. So what actually we are keeping here, sir? We are keeping some part of the page table inside the TLB. Okay, some part of the page table. Like I am saying, page 2, page 3. Page 2 where, sir, is F3, and it is, so page 2 F5. Okay, fine. And page 3 F8. Like this I am keeping inside the TLB. You can keep some part of the page table inside the TLB, but you cannot keep total page table inside the TLB. So the reason behind this one is what, sir? Because TLB is very limited in size. Normally TLB has the number of entries like what do you say this 64, okay, or 128. This kind of entries are there, but practically sometime page table has thousands of entries also, so there is no comparison. So that's why, but I cannot design the thousands of entries page table. It is meaningless. Okay, fine. That's why I'm saying that we are keeping some part of the page table inside the TLB. The reason is what, many time page table is much more bigger than the TLB. Okay, fine. Let's see what will happen. CPU generating the logical address. One second. Where it is saying that I want to access page number 0, inside that page number 0, I want to access word number 01. So we are finding whether page number 0 is available. Answer is yes. So it is supporting parallel access. Answer is yes. So this is called TLB hit. TLB hit. So that means whatever you are referring inside the TLB, that page is available. That is TLB hit. If this page is not available, that is TLB miss. That is a different thing. We'll see within 2 minutes. So now, sir, we are taking out this F5. F5. Okay, fine. And since reaching to the F5 is not a proper solution, it has some instruction like A, B, C, D, 0001 1011. Okay, fine. You have to mention that which word you want to access. For that purpose, I am taking the help of this D, where it is saying I want to access 01. So with this physical address, I am reaching to the F5, and 01 is what's our answer is D. So this architecture name is what's a simple paging with TLP. Understood this? Okay, understood this. What is the effective memory access time formula with the TLB, sir? Okay, X into, okay, this is first try to understand. This is the TLB hit. What will happen if TLB miss? Let's assume this. The CPU generates the logical address where he is saying that I want to access the page number 0 and word number 00. So is page number 0 is available inside the TLB? Answer is no. This is called TLB miss. So control will come back to the WhatsApp page table, and you are taking out the frame number, and you are making one physical address, and 1 second you are referring to this one. Then how you write the effective memory access time formula with this one? Many times students are mug upping this equation. I say don't mug up this one. Don't mug up this one. Okay. See here. In this architecture, which is the main component? Page table, main memory, TLB, CPU, which one? TLB. Because if TLB hit is there, the upper side flow is there for the execution. If TLB miss is there, the downside flow is there for the execution. Are you getting my point or not, sir? Answer is what, sir? Are you getting my point? Yes. ठीक है, चलो. Let's see, sir. That's why we are writing the effective memory access time formula with respect to TLB hit and TLB miss. Okay. So let's see first TLB hit. So X is what's a TLB hit ratio. So I'm accessing the TLB which is taking some C amount of time. After this, I have taken the physical address, and once again I'm referring to the main memory. So that is M plus. If TLB miss is there, what will happen? So 1 minus X into C. Whether it is hit or miss, in both cases, I need to access the TLB. So that's why it is C plus. You are accessing the page table which will take M amount of time. M. And once again with this physical address, once again you are referring to the main memory. So this is the formula with WhatsApp. Simple paging with TLB, effective memory access time formula. Okay, where X equals to TLB hit ratio, and C equals to TLB access time. Okay, chalo. First, we'll try to solve some problems. Okay, so I'm writing some formulas for this one. After this, we'll go for the multi-level paging if time remains. But I will make sure that time should remain. Log. page size, page table size. Where E equals to page table entry size. Okay, fine. And ninth one, page size equals to frame size. The next one here is 2 power P. Okay, and P equals to log PAS, number of frames. Page size or frame size? Because both are equal. Frame number. Okay, so we'll see this one. Let's see how to solve we'll solve some problem. It will give you some idea of this one, but try to make sure I'm giving you how much time, sir. So please take 1 minute of time and try to have some observation based on this formula. Okay. So like how we are getting the logical address, number of pages. We have seen that I'm dividing the logical address into the pages. So that's why logical address by page size. So we are getting the number of pages. How we are getting the page table size? The number of entries inside the page table equals to what's the number of pages. So that's why it is here n is there, and each entry has some size, which is called what's the page table entry size. Okay, you just refer initial 2-3 formulas for just 1 minute. So we'll see this one first one. Okay, consider the system where logical address is 27 bits and physical address is 21 bits. And remember one thing, whenever he's giving a memory management problem, whenever you are solving memory management problem, make sure that first of all you have to collect the data, because it will guide you that how which formula is applicable. Without applying even mind also, you can easily solve the problems. Okay. Page size equals to 4 kilowatt and calculate the number of pages and number of frames. So that means, okay, so we'll see this one. N equals to 2 power logical address by page size. Where it is, sir? Okay, see here. Logic N equals to logical address by page size, but logical address equals to what's the 2 power logical address. Okay, logical address space equals to what's the 2 power logical address. So 2 power 27 by page size equals to what's the? I am writing 2 power 12 because k is 2 power 10 and 4 is 2 power 2. So collectively 2 power 12, which is giving me 2 power 15. 2 power 15 I am writing as 2 power 5 into 2 power 10. So this is 32 and this is k. 32k is the answer for this one. Okay, fine. Let's see number of frames. So 2 power PA by page size, 2 power 20 by 2 power 12, which is equals to 2 power 9, which is equals to 512. So number of frames are 512 and number of pages are 32k. Okay, but sure. The next one. Go with this one, sir. Consider the system where the number of pages is equals to 2k and the page size is 4 kilo word and the physical address is 18 bits. Then calculate the logical address and number of frames in the PAS. Okay, fine. We'll see this one. Number of pages equals to what, sir? 2k. So n equals to 2k. And the page size equals to 4 kilo word. 4 kilo word. And the physical address is 18 bits. Then calculate the logical address and the number of frames. Okay, let's see how it is. If you are observing, by taking this two parameter, I can easily calculate the number of frames. So m equals to 2 power pa by page size is what's the 2 power 12. So 2 power pa means what's the 2 power 18 and 2 power 12, which is equals to 2 power 6. 2 power 6 means what's the 64. Okay, fine. The next one. With this, you can easily calculate what's the logical address because n equals to 2 power logical address by page size. If I'm keeping here n into page size, it will come here. N equals to what's the 2k. Page size equals to what's the 4k, which is equals to logical. Okay, if I'm keeping this one, this is 2 power 11 and this is 2 power 12. If I'm applying log on both sides, then I will get, sir, logical address equals to 23 bits. Okay, fine. 23 bits. Hope you got this one. How I have calculated this one. Okay, so because see, we have the less time. Hardly we have the 15 minutes, but still, that's why I am solving this. Okay, but if you want to solve, you can solve also. Okay, pause the video after the completion of the class. Pause the video and try to solve this one. You will also get one chance to solve. Go with this one. Consider the system with the logical address space equals to 128 and physical address equals to 24 bits. If the PAS is divided into 8k frames, so that means what's the m equals to 8k. Then what is the page size and how many pages in the LAS? How many pages in the LAS? That means n. Number of pages is asking. Okay, let's see how to calculate this one. See here. With this two parameter, I can easily calculate the page size. How sir it is? So I will rewrite this one as what's 2 power PA by M, which is equals to what's 2 power 24, M equals to 2 power 13 because K means 2 power 10, 8 means 2 power 3, so 2 power 13, which is equals to 2 power 11. So what page size you are getting, sir? 2 power 11 is what, sir? I am writing 2 into 2 power 10. Okay, so which is equals to 2 kW. Okay, page size equals to what, sir? 2 kW. Okay, fine. The next one. So n. So easily, since you got the page size, then easily you can calculate what's the number of pages. Let's see it is. So it is 128 means what's the 2 power 7 and m is 2 power 20. So 2 power 27, which is divided by page size kitna 2 power 11. So which is equals to 2 power 16. 2 power 16, I will write this one as 64k. Like 2 power 6 means 64 and 2 power 10 means what's our k? So 64k. Okay, fine. So this is the answer for this one, these two things. Tell me the essential content in each entry of the page table is or dash. Which one is the essential content, sir, in each page table entry? If you are observing closely, so inside the page table, what is the essential contents are frame number, page frame number, whatever you are saying, sir. Okay, this is because if you are not getting this one, if you are not getting the frame number, then how you reach to the page? Because page is available inside the frame. So it is must for you to extract the information which is called frame. Okay, so that's why answer is what's up B. Next one. Go with this one. Go with this one. Let's see what is the answer for this one. Chalo, let's see this one. Consider the system with byte addressable memory, 32-bit logical addresses. Logical address equals to कितना सर 32-bit and 4 kilobyte page size. Page size equals to 4 kilobyte and page table entry of 4 byte. The size of page table in the system in megabyte is how much, sir? Okay, page table size. We need to calculate page table size. So what is the formula for page table size, sir? Page table size equals to n into e. E he has already given 4b. Okay, we need to calculate n. To calculate n, sir, we have formula 2 for logical address by page size, which is equals to 2 power 32. Page size equals to 2 power 12. So which is equals to 2 power 20. So n you are getting 2 power 20. E you are getting 4 bytes. So collectively it is how much, sir? 4 megabyte. Since he has already said the megabyte, ignore this megabyte and take this answer. Answer is what, sir? 4. Answer is what, sir? 4. Okay, chali. Next one. Go with this one. Go with this one. A paging scheme uses TLB, translation look aside buffer. TLB access takes 10 nanosecond. First I will write the formula. Okay, a paging scheme uses TLB. Okay, translation look aside buffer. TLB access time is 10 nanosecond. That means this is 10. And the main memory access time is 15 nanosecond. This is 15. What is the effective access time if the TLB hit ratio is 90%? 90 I'm writing as 0.9. Okay, fine. 90%. Okay, fine. And there is no page fault also. Okay, Cheri. Let's see what is the answer for this one. So this collectively is what side is 0.1 and this is 10 and it is 50 and 50. Let's see here. 90% of the 60 is how much, sir? 54. This one plus and 10% of 110. 110 is what, sir? 11. So collectively it is what, sir? 65. Answer is what, sir? 65. Hope you understood this. Okay. Chalo. Next one. Try this one. Try this one. Consider a computer system with 40 bits virtual addressing and page size of 16 kilobyte. Fine. If the computer system has one level page table per process and each page table require 48 bits, each page table entry require 48 bits, then the size of the per process page table in megabytes is how much? Okay, chalo, we'll see this one. First you collect this one, sir. Collect the data. 40 bits. Page size 16 kilobyte. Page table entry. Size equals to 48 bits. Then the size of the per process page table is megabyte. So page table size we need to calculate this one. See, the page table size he has given in terms of bits. You need to convert into the byte. 1 byte equals to 8 bit. So that means what it is? It comes as a 6 byte. That's it. This is the only additional thing we need to convert. Otherwise, the total problem is like previous problem only. Still, I will calculate. Okay, don't worry. So which is what's the E actually? N equals to what's the 2 power logical address by page size, which is equals to 2 power 40 and page size equals to 2 power 14, which is equals to 2 power 26. Okay, fine. So 2 power 26 pages are there and page table entry size what's the 6 byte. So compare this 6 and 2 power 26 I am writing as 2 power 6 into 2 power 20 byte. Okay, so this is as megabyte 2 power 20. Okay, and 2 power 6 means 64. 64 into 6 means 384. So answer is 384, but in answer he has already mentioned the megabyte. So ignore this MB and the best answer is what's the 384. Option A is correct. Understood this? So we'll see this one. Assume that in a certain computer, the virtual addresses are 64-bit long and the physical addresses are 48-bit long. The main memory is word addressable. The page size is 8 kilobyte, and the word size is 4 byte. The translation look aside buffer in path has 128 valid entries. At most, how many distinct virtual addresses can be translated without any TLB miss? Okay, fine. Let's check this one. First, read this one. Try to understand this one. Virtual addresses means logical address, 64-bit, and physical addresses 48. Page size equals to the word size is 4 byte. The translation look aside in the buffer address translation path has 128 valid entries. So TLB has 128 valid entries. Okay. Like let's assume this page 0, page 1, page 2, like this. 127. So 0 to 127 I'm taking. At most, how many distinct virtual addresses can be translated without any TLB miss? Okay, fine. Let's see this one. How it is possible. See it. Try to please pay attention. This is CPU. This is CPU. CPU is generating the logical address. Let's assume this CPU is generating the logical address page number 0, and inside this page number 0 I want to access some word number, but I don't know here, since he has given only the page size, I don't know how many words are there within that page. Okay, so first I will calculate the number of words within that page. So how you will calculate, sir? Number of words in a page equals to page size divided by word size, which is equals to page size equals to what's the 2 power 13, word size equals to what's the 2 power 2, so which is equals to 2 power 11. So inside the one page we have 2 power 11 words or location or instruction, whatever you can say. Like suppose that if inside the page I have 16 words, to point this 16 to how can I represent 16? 2 power 4. To point that 16 words, I can write 16 as what's 2 power 4. So how many binary bits are required? 4. If inside the page, if I have 8 words, so that means 8 I can write as 2 power 3. So that means to point this 8 words, how many binary bits are required? Sir, 3. In the same way, if I have 2 power 11 words, okay, so to point this 2 power 11 words, sir, I require 11 bits like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay, 0, 0, 0, 0, 1, 0, like this. Okay, fine. Now please pay attention to this. Please pay attention to this. CPU generating the logical address where it is saying that I want to access the word number 0, 0, 0, 0, 0, 0, like this. Understood this? Check it. Now, with this logical address, first it is referring what's the TLB. Is that page number 0 is available? Answer is yes, available. So TLB hit is there? Yes. Is this TLB miss? No. Now next word he want to access what's the page number 0, 0, 0, 0, 0, 0, 0, 0, 1. So another logical address it is generating. So is the page number 0 is available? Yes, available, sir. That means WhatsApp for one page, how many logical address it will generate for one page? It is totally depend that inside that page how many words are there. How many words are there, sir, inside the one page here? 2 power 11 words are there. So for page 0, the CPU will generate 2 power 11 logical addresses. So in this way, how many entries are there inside the TLB, sir? 128 entries are there. So that means, sir, for each entry it is generating 2 power 11. So this is what, sir, 128 into 2 power 11, which is equals to I will rewrite this one as 256 into 2 power 10. So this is the answer for this one, sir. So answer is D. Try to understand this question, sir. The reason is this is a very good question. First of all, most of the time students are thinking that if I have one page, I am generating one logical address. No, it is not like that. Because see, it's totally dependent that how many words you want to access. Okay, in that page. So if one page has 10 words, means 10 addresses you are generating to complete all the to access all the words of that page. Okay, fine. And one more thing. Whenever in the question if he is giving the word size, please be careful while solving the problem, because it will change your game. It will change your game. If word size, instead of taking 4 byte, if I am taking 2 byte, then what can be the answer? Let's assume that's 8 byte. Let's assume this 8 byte I am taking. Just to minor change I am taking. Instead of 4, I am doing 8. So what can be your answer? So you are dividing, sir. You are dividing 2 power 13 by 2 power 3. So it will come 2 power 10. So inside the page, how many words is there, sir? 2 power 10 words are there. To point this one, sir, for one page, how many logical address you are generating? 2 power 10 logical address generating. Then how many these instructions are there? 2 power 10 into what, sir? 128. So answer is what, sir? 128 into 2 power 10. Only minor change. I made 4 byte as a what, sir? 8 byte. Your total answer is changing. So please be careful while solving this kind of problem. Understood this? Understood this? Okay. Multi-level paging is there, but I don't know. I will do one thing. Please pay attention to this. Please pay attention. I will solve, instead of explaining this one, sir, I will try to solve this problem. Multi-level paging. It is a beautiful concept. Please pay attention to this, because with this you will cover your simple level paging concept also, multi-level paging also. Okay. Now try to focus on this. How many levels of paging is required such that the outer page table fit in one page size, assuming that page size equals to 4 KB? Okay. So page size equals to 4 KB, and the page table entry size equals to, because only 2 minutes remain, so better to solve this one, because with this you will get the clarity of multi-level paging also, but at the same time you're solving problem also. Page table entry size equals to what, sir? 4 byte at all level. Okay, and logical address equals to what, sir? 64-bit. Let's see what will happen, sir. So up to how many levels you need to perform? So page size I am writing as what, sir? 2 power 12. Okay, 2 power 12. So first of all, our logical address space is how much, sir? 2 power 64. Your process size equals to what, sir? 2 power 64. And your frame size equals to what, sir? 2 power 12, because page size equals to frame size. Is it possible for you to keep this logical address space inside the one frame? Answer is no. So that's why what I need to do, sir, I need to divide this logical address space into the pages, and page size equals to what's the frame size. Okay, fine. So I got some pages, and these pages I kept inside the main memory, and the information about these pages I am maintaining inside the page table. Okay, fine. So how many entries are there inside this? Just wait for some. So I have divided this logical address space into the pages. These pages I kept inside the main memory. So information about these pages I am maintaining inside the page table. How many entries are there, sir, inside the page table? It is totally dependent how many pages are there here. So how many pages are there, sir? We don't know. We need to calculate this one. Okay, fine. So let's see. I'm calculating here. 2 power 64 by page size equals to 2 power 12. That means what's the 2 power 52 pages are there. And this here, this 2 power 52 pages I'm keeping inside the main memory, and the information about this 2 power 52 pages I'm maintaining inside the page table. Fine, great, sir. So how many entries are there, sir, here? 2 power 54. 52. Okay, fine. And each entry has some size. What is the size of this one, sir? 4 byte. So what is the size of this one, sir? 2 power 54 byte. Now, please tell me, page table size equals to 2 power 54 byte. Is this possible for you to keep inside the frame size of 2 power 12? Answer is no. So once again, I need to divide this page table into the pages, and this is called multi-level paging. Inside the multi-level paging, you are applying paging on the page table. Okay. So these pages I kept inside the main memory, and the information about these pages I have maintained inside the another page table. Sir, how many entries are there, sir? Here it is totally dependent how many pages are there. Sir, how many pages are there? We need to calculate this one. So 2 power 54 by 2 power 12 equals to 2 power 42 pages are there. And information about this 2 power 42 I am maintaining inside this page table. Fine. So what is the size of this one, sir? 2 power 42 into, so 2 power 42 entries are there, and each entry size is what, sir? 4 byte, which is equals to 2 power 44 byte. Okay, fine. Getting this? Chalo, next one. Now, please tell me, is 2 power 44 is it possible for you to keep this page table inside the one frame whose size is 2 power 12? Answer is no. So once again, we need to divide this into the WhatsApp page table, paging. So I got some pages and information about these pages I am maintaining inside the page table like this. So how many entries are there? It is totally dependent how many pages are here. How many pages are there? We don't know. We need to calculate this one. So it is 2 power 12, which is equals to 2 power 32. 2 power 32. Okay, fine. So here 2 power 32 entries are there. And each entry has size what's a 4 byte, which is equals to what's a 2 power 34 byte. Is this possible for you to keep this 2 power 34 in 2 power 12 frame size? Answer is no. But if you are observing one pattern here, 54, 44, 34, at each level it is decreasing by 2. So 2 power 24, 2 power 14. Still 2 power 14 is greater than 2 power 12. So 2 power 4. So how many levels of paging you are applying, sir, here? 1, 2, 3, 4, 5, 6. At 6th level, I am confirming that 2 power 4 is lesser than 2 power 12. Getting this? Fine. So that answer is what, sir? C. Answer is C. So with this, sir, our time is over. So we understood something about the multi-level paging. Okay. Sure.